kind of started off by saying, how do we represent words in a meaningful way? And we said that we can count and get the singular value decomposition. We said that that kind of sucked because counting is hard. So then we said we're going to use Word2Vec, right? And Word2Vec was a encoder of a word, and then you decode other words. And the only way that it could possibly decode the other words was by actually representing something about meaning, right? So it had to then develop what we would call a semantic space, okay, or a latent space, whatever you want to use. And then since then, we've been kind of stringing along ways or finding ways to combine these word meanings into sentence meanings. And we start off by saying, well, how do I just take those word meanings, get a representation of a sentence and classify it? Then last week, we looked at 2 architectures for that. Then the last few weeks, we've looked at ways of then just decoding and creating text. And that we call the language model. So that's just something where I can start a sentence and that'll kick us off, and we just follow this kind of train, so to speak, of words, and we eventually produce a sentence. Today, we're going to keep developing in that line with 2 different things, right? So it's actually kind of very semantically or clearly split in 2 today. The first is we're going to look at sequence-to-sequence models. And all a sequence-to-sequence model is a language model that is now conditioned on something else, okay? It's called sequence-to-sequence because it's going to take in another sequence, and it's going to then just start doing a decoding language modeling process that is now constrained by what it's seen in the context, all right, in the input. That's the only kind of innovation, and I bet most of you could guess how we're going to do it. If I asked you to come up here and draw it for me now, you probably could. So we're just going to keep revising and going through all the different aspects, and we're going to keep going through all the different architectures. So it starts to sit in of why does this work and why does it matter? And it's repetitive, but it eventually kind of settles down for us. The second part is then going to be attention, which is where we solve one of the biggest problems with RNNs, right? And we've already seen similar things like it when we do the encoder-decoder model or sequence-to-sequence models. It's going to become far clearer even why these problems occur and why we might want to fix them. And then we're going to show you attention, which again is the fundamental computation of transformers and all of the current boom in machine learning, even in like commerce and stuff. And so this is probably the main computation you really need to have some intuition on if you're going to kind of go forward in data science or computer science or machine learning in the next few years. So let's just look at what a sequence-to-sequence task even is. So it is some kind of transition from a sequence on the left. In this case, it's a sentence in English saying, I saw a cute cat. And on the right, it's going to be a production of, I actually don't know which language alphabet that is. But you're going to then produce a new string of tokens on the outside, right? And so the production that you produce on the right-hand side is now constrained by the sequence you've taken in on the left. Okay, so for example, translation is a natural language task, but it can be between any form of sequence. And if you're doing computer vision, you'll see that we're now even thinking of images as sequences of chunks of images. Okay, so if you can frame it as a sequence, it can very likely be shoved into a transformer. Okay, and used with a sequence-to-sequence model. So in this case, human translation is usually what we do is we take in the input X and we just go and find the highest probability production that we can, right? But this is important. It's the entire output sequence. It's all of Y, all right? It's not just X. Sorry, it's not just YI at a given time. We go and we say, what does all of X mean? And then we use that to condition our range of sentences that we can produce. And then that's kind of, we go and we give out the full Y, all right? So we're looking for the probability of entire sentences here. The problem with machine translation is that number one, we need to parameterize it, but also finding that argmax over entire sequences is hard, right? We spoke about that last week already. We did things like nuclear sampling. And so having a probability space over sentences is something that we need to find. So we have 3 questions to answer then if you're looking at it just in terms of how a machine might abstract human translation, okay? And that is, how do we get a parameterization of the distribution, all right? If you're just using a Gaussian, the parameters are going to be your mean and your standard deviation. Those are called your sufficient statistics, okay? We don't know the distribution of language nearly well enough to define it in terms of 2 parameters. So what we have to do is go throw 1,000 parameters or 1,000,000 or 1 billion parameters at the problem with a really, really flexible architecture so that it can figure out the distribution, all right? But the same intuition holds between linear regression and these models. You're figuring out parameters, and hopefully you have sufficient statistics, sufficient parameters to represent the data. Okay, so that's the first thing, how are we actually going to build the model and give it this flexibility in terms of the distributions it can define. Then on top of that, how do I go and even now define what the theta is? So I have the architecture over here. So this is the architecture question here. I have the architecture, but now how do I go and actually plug in the parameters that give me an instantiation of that architecture? Okay, and then lastly, how do you go and search over it? How do I go and use it now to find this argmax of my probability distribution? Okay, again, it's hopefully going to look fairly repetitive because we've solved similar problems already. Okay, so our standard modeling paradigm for sequence-to-sequence models is the following. You're going to have some source sentence at the bottom there in green. Okay, so this may be a Russian sentence. I think that's the Russian alphabet. Okay, and that's now going to get pushed through your encoder. Okay, and the encoder is then going to read the source sentence, and it's just going to try and represent it. So you'll notice that the encoder does not produce anything on the output side. Okay, it's completely just sucking in a representation, and it is there entirely to make information available to the decoder. Okay, it can ignore stuff. It doesn't have to use the full sentence. That's up to the encoder what it does. Okay, so it just has to build a representation of the source so that it can be given to the decoder. Okay, then you have the decoder side of things, which is now it has to go and start producing the sequence that we want, all right? The output sequence, the target sentence, okay? And that looks very much like what we saw last week, where it is just a language model. If we were just doing this, it's a language model. But now that we have this representation coming across from the encoder, it's a sequence-to-sequence model, but still the idea holds that all we want to do is this repetitive cycle of decoding, constrained now by something that's on the input side, all right? Whatever that sequence may be. So the decoder now uses the source representation from the encoder to generate the target sentence, and then that's hopefully going to match something that we can define numerically to optimize. Okay. Does anyone want to take a guess how we're going to do this? Based on last week's lecture? There's quite a few people online, so you guys can answer as well. How did we define this last week? All right, language model. What was the architecture for the decoder, and how did we use it? Yep. Okay. And then how are we getting words out of our RNN? Okay. But were we predicting one word at the end of it? Or were we going and reading the entire sentence and just producing one word at the end? Nice. Exactly. All right. So we would take in some input. So my backwards R, let's say, it would go into my RNN cell. You would produce it and you would say I. Okay. This would then be copied down here. Okay. So now you have I. This is, sorry, it's a language model, not a sequence-to-sequence model. Okay. So this would be just some initial value. Let's call it y0. Okay, you would then copy it out, and then you would go and say, well, now that I've said the word I, what's the next most likely thing I need to do? Like. Okay, and then that architecture now keeps this recurrence going through. So it has memory of the fact that it says I like. You're going to take in the copy of that next word. I like. Okay, and you're going to go and you're going to produce cats. Okay. So you start off with y0, which is some kind of noise to kick you off. You're not usually going to set it to 0, else you're going to get very bad diversity. Okay. And then what happens is you then just start producing words, and every single time we just produce a word, we copy it back in as input. So you have two pathways. This pathway says, what's the sentence I've already produced? This pathway says, what's the last word I said? And then you come out and you put your next word over there, right? You have all the information in that recurrence to try and understand what I need to be saying, okay? There is then obviously the question of how do we get y naught and how do we condition it? So does anyone want to guess how we're going to incorporate the encoder into this? Yep. Okay, how do you get to the final representation from the encoder? Yep. Yes. Perfect. Perfect. Correct. There we go. So that's the next 45 minutes is we're going to be talking about that, right? So it is exactly what we just described, okay? Except for the fact that now the RNN doesn't have an output here, okay? Why do we not need that output here? Because I already have my source, okay? The reason the decoder needs to be outputting every time is so that it can know what it once said. Number one, it's just the task we're given it, but also it needs to always have this copy back loop because we don't know what we've just previously said. I need to keep track of that in the recurrence pathway and then just so that I can produce my next word. All right, so recurrence says, what's the sentence that came before me and what's the last word I just produced? Then you combine it in your hidden layer representation to produce your next word. The encoder doesn't need to produce anything, but it does still have to take in each word, update the vector, pass it to the next one. So that this one can pass in, update your recurrence vector. Every single time you're updating the recurrence vector, and eventually, as we just said, a vector is going to pop out at the end of the sentence that's going to represent the entire sentence. There is some questions around maybe how we actually do that. Maybe the exact computation looks a little bit bad because Devin, what happens when the sentence gets long? And that's a fantastic point. But the idea holds that all we're doing is a recurrent intake of the information I need to know so that I can go from tokens to a sentence representation the exact same way as if we were doing classification. Okay? And that's the whole idea here, is this looks a lot like a classification model where usually what we would have done is taken this final layer representation and passed it into some kind of softmax, okay, some down projection into a softmax. Same idea here, except now what I'm doing is I'm passing it into my decoder, which then becomes the initial state for the language model. Okay, so it combines the two. It just combines the two architectures we've seen over the last month or so. Okay, so how do you actually condition language if we're going to look at it numerically? We just described the architecture, but in the maths. So what we want is a probability distribution over all of our sequences of tokens, okay? And so what this looks like is, again, if you have something like a independence assumption, okay, you can then say, well, no, it's actually not the independence assumption because it's conditioned. That's my bad. This is just the product rule of probability. You can break it down into the multiplication of all of the probability distributions over each of my words. Okay, so this says, I know what I said in the last t steps or up to this current time step. I know what my sentence says. What is the probability distribution over my next word? And then all I'm going to do is take the product of all of those individual distributions, all right? And then by the product of conditional distributions, you get back to the joint probability. That's language models. In this case now, we're going to squeeze in this context vector that is always conditioning the start, all right? And so that's very much going to constrain something like your y1, okay? And then once y1 and y2 and maybe y3 are actually on a roll, then hopefully they're going to start constraining my production more and more. And eventually all I'm doing is just making a coherent sentence given the input and how it started my production, okay? And so here's the general overview that we just described. You're going to process your context vector. And again, these are always going to be model specific. Right now, we're looking at RNNs. There are ways of obviously doing this with a CNN and so on. We're not going to do the CNN because we've discussed all of its problems. Okay. And so we're going to get the vector representation of the source. And then you're going to pass that through. And then you also want to get the representation of the previous token you've said over here so that you can then pass it into a softmax distribution over your vocabulary now, and then you're doing that next word prediction, right? So all the next word prediction is actually doing is classification over a much larger label space, right? It's over my vocabulary. Okay, and so this is all just going to be very flexible, but this is the general idea. You have some model that is able to take in input tokens and produce a sentence representation, be it a CNN, be it an RNN, same as when we're doing classification. Then you're going to take that final layer representation that you get out of it, again, either by something like global max pooling or global mean pooling, or your just final recurrent networks vector, and you're going to pass that through your decoder, and then you're just going to start off your language modeling process. The only difference here is that language modeling now has the sentence representation, and it's not just that Y naught or your beginning of sentence token or something like that. Okay, and then after that, what you're doing is this process of classifying over cardinality of V, so your vocabulary number of tokens each time. And so hopefully now when you get to this H vector, that is a representation not just of the previous parts of your sentence as it was for language modeling. It is now a representation of what I want to say and what parts of that I have already said. Okay, so it is a vector representation of both the source and then your previous history, right? What you've just said now, what you've already decoded. Okay, have I lost anyone yet? Are we all comfy? Do you guys remember the discussion we had last week about diversity and coherence? Yeah? What would you say the encoder vector does to diversity and coherence? Anyone online want to take a crack at it? Yep. Correct.
A lot of like this, the input is basically like
Correct.
trying to get out of
Yes. And coherence?
it. Diversity in
Correct. There we go. That's exactly 100% right. So that's the whole idea here is we are trying to constrain the range of possible things that the model can produce, right? And if we keep carrying on with these ideas all the way into transformers, then you get to things like prompting and chain of thought. And it's the same idea every single time. I want to constrain the range of possible things it can say by giving it some kind of context. It reduces the diversity, but it increases the coherence. And if there's one thing I want out of my model, that's fantastic. Okay, so that's the key distinction here is now there is a notion of correctness that we didn't have before when we were just doing language modeling, right? Language modeling, I just cared that it produced something that sounded right. The perplexity was high. Perplexity was high. Okay, no, perplexity was low. Perplexity is how confused it is at the sentence. So perplexity was down, which means that the sentence was coherent. But now I have a notion of correctness. I don't just want something coherent. I want to constrain it to be the thing that matches the input sequence. Okay, so here's the full diagram we drew earlier. So each time you're going to have still some kind of initialization of your RNN and how you take that in. So that is, again, a way to inject a little bit of diversity into this. You don't always necessarily want the exact same translation for a sentence, especially if there's not one, completely correct one. And so you may then start with different initial vectors here. Sometimes it'll be 0 if you just don't want to influence the production at all. But sometimes you may just start with random noise and hopefully that produces it. But the whole idea here is that I am now going to keep track and keep embedding each token over and over and over. And now by the time I get to the end of it, I have a single H representation for my entire input sequence. All right, same idea as the classification, but now that is a lot of information that it already has that when I pass it through into the decoder is now going to start constraining the production. Okay, so now I have the beginning of sentence token, which information stream I have now is what I want to say. Okay? And so what I want to say is then going to kick me off and start the classification over my vocabulary, that cardinality of V, representation we've had above, or notation we had above. And so I'm just going to say, well, I know that the sentence I want to speak about is in the first person and it's about the subject, okay? It's very unlikely that this token here has completely remembered perfectly that backwards R is the first token that we need to embed, all right? It has a far more semantic representation of the sentence or the input sentence, but at least it retains that information, or hopefully it retains enough information that I know that starting a sentence with I is a very likely thing to do, okay? In the language modeling sense, we do not get that constraint. So now I'm just sampling randomly from all possible first words. Okay. You are not going to go and start a sentence with a verb. So your language model should hopefully know that, but it's going to start with any form of article or noun or whatever. Now we can't do that because I am constrained. I have lost that level of diversity for something that is going to hopefully be far more coherent as I produce the sentence. And that coherence is what makes it a sequence-to-sequence model. It makes it bound or relevant to this translation task. Okay, and so all we're going to do is then keep doing the same process. I produce a word, and then I'm going to copy it down. Let's use green or something else. Okay, and I'm going to copy down the word I just said. Reason being, this vector does not know what I just said. So I can't rely only on the recurrence. I have to tell it what it just said. Essentially, it's like it's listening to itself as well. And so then it says, well, whatever I said up to now, take the last word, combine it with your sentence representation, and then you know that, oh, okay, I've already said that I saw something, but the sentence requires me to actually say a noun. What was the context? What did the context speak about? And the context was speaking about a cat. So I'm now constrained to produce a sentence and language model that is only now relevant to me seeing a cat. Okay? And it's then after that, it's the same idea as the language model from last week. Next word prediction over and over and over. Okay? And eventually, like we did in class, someone will say full stop or someone will say end of sentence, and then you're done. All right? You just stop producing when you see the EOS token. Does this make sense to everyone? I'm not seeing a ton of nods. This is really important, so we can spend time here. Yeah? So the encoder is trying to combine the token representations for the words into a single sentence representation, right? And in the same way that when I'm speaking to you, if I asked you, what was the word I said 10 words ago? You probably can't say that, right? You weren't tracking it. It wasn't relevant to you, but you still understand me. So this vector is understanding. Please don't anthropomorphize it. So the hidden state is your understanding of the sentence. Okay, your individual tokens are the exact words that get said. Now, it's probably not tracking individual words any more than you and I are when we speak. So it's tracking something like a semantic representation of the sentence. It's extracting the meaning. The problem is that now when I go to I, it needs to say, well, what was the most likely individual word to match another individual word on the input, even though all I had was semantic, that sentence representation. Okay, so it's a little bit of a hard task. You don't say I is the exact right word. It could have been me, it could have been I, it maybe could have just been he or she or whatever. So constraining one individual word to be highly specific to another individual word is really hard. Does that make sense? Okay. Any questions? Cool. Okay. And what's nice about these things is you can essentially think about it as now something like a big word2vec, because word2vec encoded a word and then decoded a word. Now we have something that's encoding a sentence and decoding a sentence. And so what did we do in word2vec? We went and looked at that layer between the encoder and the decoder that caught all of our semantics. And we said, well, I can manipulate them, I can look at them, I can interpret them, and I can hopefully plot them into some kind of low dimensional representation. And if you're taking data visualization as a class, I'm sure by now you know all about PCA and TSNE and UMAP and all these things that people use to try and represent vectors intuitively. And we're just going to do that. Okay, we're just going to take the final representation out of my encoder, the thing that says what meaning, what is the ultimate information I need to hang on to. Maybe some details are lost, but what is the overall point that I need to make? And I'm going to go and I'm going to plot this, and I'm going to look and I'm going to see that it has a lot of really cool structure. For example, at the bottom left of this 2D plot, which again is really low embedding, you will get something like John admires Mary, John is in love with Mary, John respects Mary. As I move to the upper right-hand side, you'll get Mary admires John, Mary is in love with John, Mary respects John. So what we can say here is that this axis in the latent space, in the semantic space, flips the subject and the object of the sentence. Okay, and so we can now say this is great. I have a direction that I can manipulate if I want to say maybe Mary is now the subject rather than the object of the sentence. Okay, which is good. I can manipulate these things, I can interpret it, and the fact that it has encoded subject and object relationships means that it has an underlying understanding of grammar. Okay, again, understanding, it's represented grammar in its latent space. Okay, and so that's really important to know. And it turns out that if you go and you know, there was this one paper, and there have been many since papers that have shown that this is a highly structured meaning space of representations. And again, that is the whole point of NLP. How do you take something that is completely meaningless, like a symbol, right, like a word, like a set of letters, and get something and encode meaning into it? Okay, and this all goes back straight through to the distributional hypothesis. Okay, we are still just doing next word prediction. We are still just saying that words that come in similar contexts must mean the same thing. Okay, and you can see that here now more than ever. You're taking in some context, and that is going to constrain the set of available words you have for you to produce in your decoder, and those are going to be only the words that are in the same semantic region. Okay, in the same area of your latent space. Okay, and then so you can interpret more of them. You can go read these and have a look. They're nice examples. So that's the model. All right, so we've parameterized something. We have a network that can produce a distribution over words. All right, but how do I go and get the parameters now? The same way if I wanted to fit data with a Gaussian, I'd have to say, where is the mean? What's the standard deviation? I now need to go and find the thetas. And so how do we do that? Well, this we've seen over and over and over. It's the same way we trained classification. It's the same way we trained language modeling. And now it's going to be the same way we train sequence-to-sequence models. You have some example output that you wanted to follow. And again, in this case, because we are looking for something highly coherent with low diversity, it means that there is a very clear target sequence, right? Especially in something like translation. This works really well for training because we get a very clear, very constrained learning signal. All right. So we know that given the source sequence on the right here, and the fact that you've already said I saw A, means that you have to start speaking about cats next. And we will have this as an example in our training data. All right. So our training data is going to be pairs of input and output sequences that it's now going to be trained to imitate. And so it's going to learn, and it's going to say that given the fact that the input sequence is, sorry, wrong. Given the fact that the input sequence is X and all the stuff that I've said before, all right, let's do, how do they represent, oh yeah, Y. Y, I less than T, whatever. All right, how do I now go and represent YT? Okay, that is the now distribution that we have. So it says constrained by the context that I'm given, constrained by all the things I have previously said already. What is the only thing I need to say next? And you're going to go and you're going to say, show it what it should be saying. Okay, that is going to come out of your model predictions over here. Sorry, I did that wrong. That comes out of your model predictions over there. All right, you can see that it's saying, given the fact that I saw A, so that's this bit over here. Given the context that was passed in, that's this bit here. What am I doing? I am now getting a distribution over my vocabulary over there. Hopefully, it's going to say cat is really high. Hopefully, it's going to put a lot of probability on that one token, that cat token. But in this case, it doesn't. Okay. That probability was low. And so all we're going to do now is say, well, I need to then increase the probability of the token that I wanted to see in the example and decrease all the other ones, especially if they confused it. Okay. And so it's going to pull down all the other tokens. That is just saying maximize the probability of cat, and you will do the negative log so that it becomes less explosion-y from the exponential in the softmax. And then you can do the negative so it becomes a minimization process. Okay. So all you're going to do is take the output probability for cat from your model, negative log it, and then you want to minimize that negative log probability or the negative log likelihood of the correct word. And why can we only do the one word? Because the target is 0 for all the others. So because we have this really sparse label, we don't have to go and actually manually intervene into all of the other targets. Just by boosting cat, the softmax will pull down all of the alternatives. Okay, and so we now end up with a probability distribution that favors cat. Next time we condition it on the same sentence. Okay, and that's the whole point here. Again, it's conditioned on that sentence. All right, we all following? Before I explain cross entropy again. Okay, there is one more aspect to this that we need to consider, especially now that we are trying to be so constrained and we don't have the flexibility or the diversity that we had last week. So what we're saying we want is we want to get the argmax over our entire sentence. Okay, and so that is this argmax y over the product of all of the conditional probabilities. Again, that conditional probability is just the probability of the next word run through our neural network. Okay. And so what we're saying is that at each step, I'm just going to pick the token with the highest probability, but that doesn't look the same way if you actually write out the equation. Okay. If you write out what we're doing this bit on the right-hand side here. You're taking all of your previous context, your y less than t, and your x, your input context, and you're producing the next word, but you are sampling greedy, right? You're saying, I want to pick yt. We are not picking the full sentence as one coherent thing, okay? And unfortunately, those are not equal, all right? Just saying, I'm going to pick the next most probable word does not give you the most probable sentence, okay? This is a big problem. And if you're working in diffusion models now, this is entirely why we are now working with diffusion models in NLP. All right. We're not going to go too much into diffusion in this class, but the reason is because diffusion does optimize your entire sentence at once. This next token prediction, YT here, does not actually give you the most probable sentence. It gives you the most probable individual words. Okay. This is called auto-regression. All right. When I'm using the previous output, my own output, so it's auto, it's something I've done, to produce an output, so regression, I'm doing the logistic regression or the softmax regression over my vocabulary. So I am using my previous predictions to give me my next prediction, all right? That's auto-regressive, and you will hear a lot of people lately saying auto-regression is a big source of hallucinations and all those things. Why? Because if I find one really probable word over there, right? So if I go and I say, the Sistine Chapel is in, and I go and I pick London, right? I've picked a highly probable word. Lots of sentences say London, all right? It wasn't really well conditioned, but let's just give me a break with these examples. So I've now picked a word that seemed really probable. The problem is that now I cannot ever produce a coherent sentence after that, okay? Everything I say after that is now going to be incoherent. If I go back to speaking about the Sistine Chapel, then it's going to be wrong, all right? Because now I'm not speaking about London anymore. And so you can always pick a word that looks good, but will eventually lead you somewhere else. This is a fun trick you can do in language modeling as well with humans. You can, there's these sentences called the golden path sentences, right? One of them is if you say, let's eat grandpa, right? You need to know where the punctuation lies. But as long as you're now kind of following through with that decoding, the meaning of it hinges on this one individual choice. And if you make a bad choice, then you're going to be in a problem, right? So if you don't put the comma there, now you're actually saying in your sentence that you want to eat your grandfather, which is a problem, right? And that is now going to say, well, you need that YT to predict a comma, and that is a mistake that can be made. Okay, so we don't necessarily know that we are going to get the most probable sentence out of it. And so the way that people have started handling this, and it has a really big downside, specifically with transformers, so this isn't really used anymore, but it was at the time, is to do something called a beam search, right? And this is a basic search algorithm from computer science. And the whole idea is that you're going to try and keep several candidate sentences in mind at once. So you're going to start with your beginning of sentence token. That's just straightforward. And you're going to say, well, what is the candidate set of words I could choose from? So you're not going to commit to one word up front. You're going to have this hyperparameter called beam size. And those are the number of words you're going to keep. So in this case, beam size is 2. All right. So you're going to say, well, I can start the sentence with a or the. Then I'm going to produce 2 more words for each start. So a cat, a kitten, the cat, the kitten. Great. Both of them seem to go the way of cat and kitten. This is likely due to it being constrained by the same context. But now you can see I have 4 possible sentences there, which means that this is now getting to be a really big thing that I have to hold in memory already. I don't want to have to think around a cat, a kitten, the cat, the kitten. So I'm just going to drop back down to my beam search size. All right. So in this case, I'm going to go back down to my top 2 hypotheses. And for argument's sake, let's just say that the top 2 most likely set of both words is the cat and a kitten. Okay. And again, that probability or likelihood of both words, that can be measured with something like perplexity. That's just then filtering in the full sequence again and saying what's the probability of seeing that sequence. All right. It's like surprise at reading that sequence overall. So now you're saying, okay, I was least surprised by a kitten and the cat. So I'm going to now only use those 2 to produce some more candidates. And so now we get 2 more candidates for all of those sequences we've already created. So a kitten sat, a kitten was, the kitten sat, the kitten was. All right, we're back to 4 sentences. So we're going to go and see which 2 overall are most likely. Okay, and so a kitten was, the kitten sat. And eventually we're going to keep rolling out this process over and over and over until eventually we get to 2 sentences that now are candidates overall. But you can see we've tried a whole bunch of sentences along the way, right? At some point we were considering a kitten was on a mat, and I didn't want to say that. So I then went with a kitten was on a rug. End of sentence. Okay, so every single time there are these candidate sentences that we hold in memory very slightly for a few minutes, and then we go and say, well, I'm going to rule those out, and I'm going to hang on to only the 2 that I like best, right? Or the N or the K that I like best. And then we end up with a cat was on a rug, or the cat sat on the mat, and now we just have 2 candidate sentences, and so we're just going to pick one that we think fits the context the best. Okay, it's the highest probability sentence. And so now at least we have a process that is doing next word prediction, but it has this higher level mechanism to check the sentence I've created overall, and we just hang on to those sentences. All right. The problem is that this requires a lot of memory, and especially if you're working with something like a transformer, you're going to end up very quickly making many candidates. And so you also need to usually set the beam search really high so that you can hold on to all the possible candidates that the transformer can produce. And so current language models don't use beam search, but in the old days when we were doing slightly shorter sentences, this worked really well. Okay, so it's important that we understand that beam search is a thing. I think it's important that we understand its pros and its cons. And mostly I want us to understand that autoregression and predicting the best, most likely candidate sentence are not the same thing. Okay, the right-hand side is autoregression, the left-hand side is global optimization. All right, and this is really important for modern days because this is the whole debate of diffusion versus autoregression. And what you'll find now is Google actually made a diffusion gemma recently that does both. So what diffusion gemma does is it optimizes this in blocks. So it gives you very coherent blocks, and then those blocks are put together autoregressively. So it diffuses phrases so that it gets this globally optimized, like really coherent phrase, and then it goes and strings phrases together because we don't actually know how to efficiently global optimize a sentence. Okay, that's the reason why we need to do next word prediction, is because getting the full probability over all of our sentences, for example, like a beam search taken to the max, is going to be almost impossible. Okay, does everyone understand this trade-off? Okay, next word prediction versus full sentence probability. Okay, next word prediction is an abstraction of it. It's a computationally more efficient way of doing it, given the assumption that you're not going to go too far off. Okay. So I think it's time for a break. When we come back, we will speak about attention. All right, I'll see you guys at, let's go slightly longer. I'll go 1:15. Guys online, can you hear me? Alrighty. Okay, so now let's look at attention and why we even need attention. So there are kind of a few big issues with recurrent networks. We discussed them initially when we were doing classification. Okay, but now we're going to go a little bit deeper into them, and they're similar. They're not all exactly the same. But the first is that we have a fixed size vector to represent our context with, right? And so that is a really, really difficult thing to do as the sentence gets longer. This we did see when we were talking about classification, right? We said that there is a lot of kind of stuff that has to go in there, especially if you're doing something like sentiment analysis on a paragraph. And so it's the same exact idea, except now you have to squeeze in all of the information you need, not just to classify something, but to actually produce next words. And so this is what I was saying earlier when we were saying, well, what's the issue with producing the exact word I on the output? Well, it's very unlikely you're going to remember the exact word you started the encoded sentence with, right? That is a very unnatural way of doing things. And as the sentence gets really, really long, you're going to start overloading and putting too many vectors into that representation. And so you are going to start incurring noise, all right? There was also the problem of the fact that things that came on the left of the sentence get forgotten earlier than things on the right. Okay, so the way we can talk about this is that there are really two issues. The first is that the encoder has a really difficult time trying to compress all of the context into a single vector. Okay, the decoder then also needs different information from that compressed vector for every word it's producing, right? It doesn't need to remember the fact that the first word was I when it's moved on to talking about the cat. Okay, and so it does have a little bit of a mechanism here in its own recurrence to say and update what part of the memory remains. Okay, and so its own recurrence does kind of start forgetting by deliberately forgetting aspects of the sentence. So it says, I have produced the word I. So now for what I pass forward, I'm going to forget that that is a specific word that was maintained. Okay, so it can start to update it, but that is a really, really difficult thing to do in a recurrent matrix operation. And rather, we want it to be able to find the specific details on the input that it seems to be losing. Okay, so what the decoder doesn't need always is a summary, which is what the encoder is giving it. What it needs is specifics plus the summary, where the specifics are relevant to what it's doing at a particular point in time. Okay, so to summarize, the encoder has a hard time putting all the information into one vector, and the decoder can sometimes have a difficult time retrieving the details out of that vector. Okay, and so what we're going to do is we're going to introduce a new mechanism, which is called attention. All right, and it is literally called attention because of this ability to go back and pull out details from the input sentence. All right, so it's where you're actually going to put the focus of the model. All right, the focus in inverted commas. Okay, so let's say this is how far I've gotten in my RNN, right? So I took in the sentence, I saw a cat, I saw a cat on mat, all right? And now you want to go and produce it. So you've said, I saw a, on the output, you need to go and think around what the next word is. And the next word needs to be cat, all right? But now again, if you're representing the semantics of that sentence, Cat is one word and it came fairly early in the sentence. So now there's semantic representations for what it was doing, such as sitting. There's semantics for the fact that a mat is involved. If you went and carried on with the sentence afterwards, now there's semantics of the fact that it was looking at a dog. And so now there's a whole bunch of stuff all squeezed into this vector. And I need to try and retrieve it, not only from that vector, but all the 3 or 4 updates that have happened as it's been decoding on and on and on, including keeping track of all the stuff it's already said. When all I really need is to go and say, well, what was the word? At this point in the original sequence where I am now, what was the word? And then you can say it looks like something like kato or whatever it is, katio. And so now you can then go and just copy it out. And so this is the mechanism we need to do. So what we're going to do, I'm not going to tell you what the computation is yet, but those blue dots are some kind of mathematical computation between the vector that I currently have. All right, so it's my current H, it's my current semantic of the full context and everything I've said before. And I'm going to then go and dot product it with the vector representation on the context side for every word. Okay, so I'm going to go and take that dot product of my current vector with every single H vector that I produced while I was encoding the sentence. Okay, does this make sense so far? All right. That is then going to get passed through a softmax. Okay. So I now have some kind of scalar representation for the for the operation between my current vector and all of the individual other ones. Switch to blue for sanity. Now I'm going to say, well, that operation gave me a scalar value. That's the only requirement I have on the blue dots, is that they are scalars. And then I'm going to pass this through a softmax distribution. All right. Why a softmax? Because I don't just want to now have some scalar that is diffuse across all of the representations. I want to force it to tell me about one thing in particular, for example, the cat. So a softmax in this case is literally doing what its name says. It is giving you the max representation, but I don't want something that's actually a max because that's not differentiable. So I'm going to do a softer version of it. All right. So I'm going to start to squeeze around 1 or 2 very high likelihood or very helpful candidate words. For example, the word cat. Once I run it through a softmax, right, I now have essentially a probability distribution or just a normal distribution around which input words I should be looking towards. Okay. And that is going to be, in this case, cat or kato. All right, because that's the next word that I want to produce. That's the one that's highly, highly likely. Okay. And that weighting is then going to be used to give me a weighted average of all of those context tokens, all of the context tokens. So I'm going to take this context token, I'm going to multiply it by its own scalar value after the softmax, right? So this value here, and that is going to get added to a representation of the vector, all right? So this is the weighting here. This is the average that we're taking it over, is all those input vectors. Okay, all those context vectors of the sentence at that time. You will notice, and you will probably be saying, oh, but the recurrence is happening at the bottom here. So this information still contains, or that vector still contains information coming from the left. That means it's a bit overlapping. Yes, 100%. All those problems you're describing of the fact that this is still a recurrent representation of the sequence at the bottom is going to be true. But at least what this is a way of representing the fact that the word I just processed, all right, the fact that you have EOS or whatever, the fact that I just processed that word and it updated my representation to be more useful or more similar to the representation I have that I'm currently trying to decode from, means that that word must be something that I should care about. It means that it's useful, all right? And so that's all that's happening here, is you are trying to just get some signal on the input for the fact that that specific point in the context was important. And then that is now going to be used to weight it up. So in this case, cat is essentially the only vector that gets a really high probability. And so it now dominates this weighted average. And so this is a vector that essentially looks identical to that representation for cat that just came through in the bottom. Okay. That then gets passed into my decoder. So it gets combined not just with, well, it gets combined with the H vector I currently have. So it's the vector that I'm currently trying to decode from. It gets combined somehow. Most obvious version is just concatenate them, and then best of luck to the neural network to figure out how to do that. So it gets passed to the decoder, and now it is used in some way to influence the probability distribution of your next tokens. Okay? But again, the whole point of it coming from a sequence is like really parallelizable checking of what information am I currently dealing with, and when I was dealing with the context tokens, did they have similar information individually? Which tokens are most likely to be useful for what I'm currently decoding? Okay, now we're going to get a distribution over them so that I don't just boost everything. I want it to be selective, so I pass it through a softmax. And then now through the softmax, I have retrieved only what should be highly relevant information to what I am currently doing in my decoder. Okay, I then put that back in. So I have my global representation. Let me clean this up a bit. So I have my global representation coming through the decoder recurrence. So this is still doing its job. I still need that information, right? I still need it to say what the full context semantic is and what parts of this have I already decoded up to now. That's still useful information that attention cannot give me. You'll see that the attention has nothing to do, especially with these red tokens. So the language modeling is not sitting on the attention here. The language modeling is still sitting on this recurrent vector. All this is doing is saying, go and find a bit of useful information from my context and make sure that I have that as a very salient vector representation. All right, go look for the details. Look for the fact that I'm talking about a cat rather than just the general notion of speaking about a cat. Okay, and so now I have both. I have my general semantic, the intent of what I want to say and what I've already said, plus the details of what exactly I am translating or what exactly the context requires from me. That then is used, or comes to that now, that then is used to produce the next word. We don't get it, but essentially here, that then should produce cat. All right. After that, it's just the same thing. All right. So usually you would have taken this vector here, passed it into a logistic regression over your dictionary. All right. This is the cardinality of V. Same exact idea, except now all you're doing is taking in both the red vector over here and your green context vector that are now concatenated together. All right. So it's still just a usual forward pass into a prediction over your dictionary after that. Okay. A lot going on there. A lot of little moving around of bits. Does this make sense? Can I answer any questions? It's important that we understand this in the recurrent sense, because when I come to teach it in the transformer sense, there's a few details that make it a bit weird. So we can, well, not weird, make it work really well. But we can linger here if this kind of idea of the backwards computation and softmax doesn't sit well. Yeah. It's both. So it's the usual recurrence step, which is take in X and then the H that I have. So it's that recurrence stream coming through plus the X, and then usually kind of you then concatenate to do the next word, right? It's the usual recurrent step that we have. Okay, so in the recurrent cell, we would usually just have this square here. You would have your X at your current time step plus your H at T minus 1. They're going into a neural network over here, but the way that that goes into that neural network is to also try and just concatenate those two representations. So you can then do next word prediction over here. All right, so that's X T plus 1. That makes sense? That's the usual computation in the cycle over it. And then now we're concatenating the third thing, which is bring in this the context attention vector, which I'm just going to call AT for now. Okay, so you have the three streams coming in. You have your input stream, you have your recurrent stream, and you have your attention stream over there. Cool. Any other questions? Okay. How it combines them then is just the big question, right? Like that is obviously going to be a big challenge because now you have more information to try and decipher. All right. And so this is also why we need a lot of data to train these things, because I just have now a ton more operations that I can do on a single vector. So it is now less easy to identify what is needed. Let's say I produce an incorrect word over here, right? Is it because I didn't encode the word properly? Is it because my recurrence was bad and I lost scope or I lost track of where things were? Or is it because now I just attended badly to the input tokens, right? So this is the difficulty of it, is now it's less identifiable what's going wrong. And so you're going to need more input data to try and decipher that. Okay. The one really good news about this is that this computation here is done individually on these vectors. All right. These, you do not have to know one vector to the left before you can do the one to the right, the same way as when it's recurrent. So you can do that computation completely in parallel, right? Which is really, really useful because that means it's very quick. So it doesn't slow down our ability to generate words. And so we are still bottlenecked in generation speed by the recurrence, which means that we can still churn through a lot of data. Okay. The only issue here is that we need more of it to try and figure out how to represent these vectors. And that is ultimately what gradient descent is going to be doing. It's going to now not just be trying to figure out how to represent the sentence as a semantic over here. It's also going to start learning to represent vector representation on your encoder that makes it easy to find it later on by attention. Okay. Gradient descent will do that. Again, that's what the kind of lots of data is there for. So now it doesn't only say, what have I represented in my sentence and what am I currently talking about? It's also going to figure out that it will help if it has this part of the vector space that makes it easy to find later on. And so it will start to learn this kind of mapping between the decoder latent space and the encoder latent space and make sure that they stay aligned the entire time. Okay, that is a really difficult thing to do still. That is still squeezing so much into one vector, right? It's now not just saying, remember what we've said or encode the semantic of the sentence. It's also now saying you want to do all of that plus be findable later on by the decoder. Please represent some aspect of your vector space to just signal what you are talking about. Signal the fact that you just encoded the cat, right? Then when you move on, signal the fact in this vector that you just encoded math, and then use the recurrence to try and coordinate between these two things. It is a really, really complex operation, and so we need lots of data to get around it, or you need to do it slightly smarter, which doesn't require recurrence, and that's eventually where we come to transformers. Okay, so there are still one or two lingering issues in how these vectors actually signal what should be attended to, but we will get there. We will solve that in a couple of weeks. Okay, if that's, again, it's not going to be intuitive to start. It never is with attention. If that is sitting slightly comfortable, we can move forward, or I can answer some questions about it. No questions. Okay. So let's look at what mechanism we actually have here. So you can see it's already showing you in this box on the left. So you're going to take in your kth encoder state, all right? And you are going to take in the current time step of your decoder. And all we want to do is have some attention function over here that will produce what we call a score, okay? So the score is the dot. And the word score just comes from probability theory, because usually it's kind of, or your score is kind of the thing that goes into your exponentials in a softmax. Okay, it's if you log a probability distribution, you get the score, and you'll see that now come up in diffusion models as well, because they work directly on the log of the distribution. Anyway, so we need some computation that is going to take in our encoder states one by one and the current decoder state and give us these score values, give us how likely, or, you know, in my words, what I've been using in this course, this is something like propensity. Give me the propensity of these two vectors being useful together. And again, propensity is meaningless on its own, all right? It is just some value that when put in context of other values will make sense as a probability, okay? So all the score has to say is how relevant is my source token K for my current time step that I'm decoding. Okay, you get the propensities or you get these scores. They are synonyms in my case right now. And so what we're then going to do is say, well, I have all these numbers. They all popped out and it said that time step K in the context was really relevant to what I want to do. It's 1,000. And it looks like all the other time steps in my context was 10. All right. So it's orders of magnitude larger in terms of score than anything else that I had. But I don't know what to do with that because that number is meaningless. Do I now go multiply by 1,000? Probably not. So we're going to run it through the softmax and you get the probability distribution over these tokens. How likely or how probable is it that this word in my encoder is useful? Okay. And so the good news about this is when I use this as a weighted average, it's not changing the magnitude of my latent space. Okay, all of these vectors, all of the S's and all of the HTs will stay roughly the same magnitude because it's just this weighted average where my weightings are now probability distributions, and so they will sum to 1. Where my weightings are from a probability distribution and they sum to 1. Okay, and so that is then called your attention weight for that source token K at time step T. All right, please keep track of the words that we're using here, right? So you take time step K in your context and you take your current decoder and you get the score. Then you run the softmax to get your attention weighting. And that is relevant to a single source token and a single decoder step, which is the one I have right now. You can see it's denoted as T up at the top and K up at the bottom. Okay, so your attention weight is the output of this softmax over your input sequences relative to what I'm doing right now. All right, those are your weightings, and then all you do is copy out your original vectors all the way back here and do the weighted sum or this kind of weighted average of the of those source tokens. All right, multiply by the probability that that token was useful times that token by that probability, and then just add them all up. All right. If a token wasn't useful, then what's going to happen is that A weight is going to be close to 0 over here, and so it doesn't contribute. All right. Why is it close to 0? Because the softmax is going to pull it down. All right. If it didn't have a really high score or another input context token did have a much higher score, that division by that exponential is going to pull it down very, very quickly. And so you're going to have this really sparse set of attention weights. Okay, they may not be exactly 0, but they're going to all be really close to 0, except for hopefully 1 or 2, and then they're going to be large, and that's going to upweight this representation of maybe 1 or 2 encoder vectors. Okay, does that still help? Are we still following the different computations? Okay. Okay, and so this is then the whole point of this is that now we are also letting our model decide to pick its tokens. Okay, so for every single time it says that I just said the word I, and I can go and look back in my context for specifics, and my recurrence channel is telling me the semantic of the entire sequence, and I know what I just said, so I can combine that into my current sentence representation. And so I know that I want to say the word saw after that. And then once I've said I saw, you now go back and you can attend to what was in the encoding to see what did you see, and it was A capped. All right, and you can just follow this process on and on and on. But you are now putting pressure on the tokens, right? There is a new requirement sitting on these hidden layers, and that is to be able to coordinate through this computation. Okay, you are still going to now learn a decoder representation and an encoder representation that is able to give you really useful weightings at the end. Okay, and that has to come through the same mechanism as everything else, which was next token prediction and a label on that sequence modeling step. Okay, but at least now there is a computation that could potentially allow it to copy stuff out, right? When it gets to the end of the sentence, it can go and attend to the EOS token over here and say, well, when I got to this point in my sentence or a similar point in my sentence in the encoding, what did I do? I ended. And so now I'm going to end as well. All right. So these kind of like representations of where are you in the sentence and what semantics are there and what parts of speech are there, they all become useful now for understanding of identifying what one token is useful. Okay. Assuming that it can be learned. All right. So we now need to just define what mathematically is actually going on in this score function. And it's actually really intuitive. There's nothing too much to it there. The most obvious one, and the one that we use in transformers actually, is just dot product. Okay, again, we know that with the dot product, if two vectors point in the same way, they will be large. And then if they point in opposite directions, they will be big and negative, which means when they go through the softmax, all right, that's exponential of a negative, it's going to go really low. That's why we use the softmax on our propensities, so that negatives now make sense. And then if it's orthogonal, if they're doing completely different things, then you're just going to be close to zero. Okay, so that is just the most obvious, easy way of saying, well, how do I represent similarity between two vectors? What am I doing at the moment in my decoding, and what was I doing at the time in my encoding? Okay, that's the most obvious way of looking at it, is you're just tracking where you are in the sentence as you decode it and going back to that exact word on the input side and saying, is this the right word to be focusing on? Was this the specific thing we were talking about at this same point in the sentence when I was encoding, now that I'm decoding it? Okay, and it is very close to what's going to happen if we were doing translation, right? If I spoke to you in Russian and I asked you to translate it, you would go back and you'd say, well, I have to say the word cat. What's the Russian word for cat? Or I have to be speaking about something, and at this point in my sentence, what was I speaking about? Oh, I was speaking about dogs. I'm going to speak about dogs after 4 words in my new sentence. All right, it can be very spatial. Okay, and that is the most obvious thing that it's going to do, is it's just going to track where you are in both sentences and maybe upweight spatially what was on the encoding side. But it doesn't have to be that. The neural network can figure out whatever way it wants to help you identify information on the input side. Okay, the other way you can do this, so there's 2 more ways. There's the bilinearity. Okay, so it's just a generalization of the dot product. Okay, dot product, I'm sure you guys know this, but just for clarity, dot product is just the bilinearity where W is your identity matrix. Okay, then you get HT transposed times by I times by SK, and I can do this computation first, and so you have HTI SK. All right, which is back to just the dot product. So the identity mapping doesn't obviously change anything. So the bilinearity is just the generalization of your dot product to say, maybe this just isn't Euclidean space. Okay, maybe we're in something a little bit more complicated. And so I want to have some kind of like metric representation of that. And those are just learned weights. All right, W just going to be the weights of your attention. Hopefully backpropagation can now figure that out. All right. And then taken to the full extreme, you're just going to use another neural network. I have no idea what the score function should be, so I'm going to parameterize it as a neural network and give it a whole bunch of nonlinearities so that now it is a universal function approximator. So whatever could be a good score function, my neural network has the capacity to represent it. And so now I'm just going to hope that with enough data, it will find it, right? Those are 2 different things. There's what it can represent and what it actually does represent. And so in this case, all you're going to do is you're going to take your 2 tokens that you care about their similarity. You're going to concatenate them, and you're going to run it through a small neural network that is meant to give you a scalar on the end. Okay. And that scalar becomes your score function. Okay. This works if you think about it in terms of then those scores being fed into a softmax. This works almost identically to our ideas and intuitions of classification. All right. If you're doing the multi-layer perceptron, all you're doing is this really small classification problem of what should I be looking at on my input. Okay, it's not coming from necessarily a label, it's coming from this back propagation over here. But still, if you get the word right, that means that you know that your attention classification was good. And if you get the word wrong, then your attention classification was really, really bad. And so you can hopefully start to learn the parameters of all of this that make the next word you want to see more likely. Okay, same intuition. All of these operations are now differentiable, and it is just about pulling them back with gradient descent and enough data to accommodate them. Okay, does this make sense in isolation, let's say, regardless of how it fits into attention mechanisms? Do we understand how taking the dot product between my current context vector and all of my other context vectors will tell me at least which previous context vector had a high score? Right, ignoring what score means. Does the dot product make sense? Okay, the bilinearity, that's just a generalization of that notion to a little bit more complicated vector space. Doesn't matter, it's learned by gradient descent anyway. I will never know what that vector space is. Same intuition, it's just giving me are the two vectors facing roughly the same direction. Okay, and then MLP, if I don't even think it's a linear operation, if I don't even think I'm in something like a vector space, then I'm going to have to do a non-linear way of getting to the score. And so I'm going to throw it into a neural network and really, really, really hope that those weights over there can be figured out with some data and gradient descent and backpropagation. Okay, and this is the way I would study this. This is the way I would look at it for now. When we go to attention in 2 weeks, you will realize that they clean up a lot of the machinery of this. Okay, or in 3 weeks, they clean up a lot of the machinery of this, but it's a very similar idea. Okay, all we're doing is this really repetitive operation over and over and over, and that's going to allow me to identify useful words on the input. So this operation came from a paper by a guy called Badanu. So this is considered to be the founding of attention. And so we're going to look specifically at two architectures now and how they actually do this, as if they're, I guess, little case studies of attention. But there is flexibility to this, right? It's more like, for lack of a better word, a framework. Okay, so it is how you incorporate the attention. There are some design decisions that we can just make. Okay, so in the Badanu model, number one, they didn't just use the recurrent net, they used the bidirectional recurrent neural network, right? Why does that help us? Someone remind me why we might use a bidirectional recurrent net? Yeah. That's one of the things. But what gets lost if we just go left to right? Yeah, exactly that. So you will forget the parts of your sentence that came earlier on. And then also we may use this to now to represent things like parts of speech. And so now you're forgetting the subject of your sentence. So they start by saying, okay, bidirectional RNN is a useful thing. And at that time, they were very popular. So now we have a better way of representing the input tokens and not forgetting a ton of information. Then they feed that. That's the encoding. But what you will notice here is that there's no very clear way of how to encode the bidirectional RNN. This is his biggest weakness, is that this pathway is going away from where we want it to go. All right, so we can't really do much with that right now. And so this is also one of the motivations for attention, is we just have to take that last sequence. We just have to pick one, okay? And so now that backwards RNN is not really doing much for our decoder. And how exactly to get that to do much for our decoder was unclear. You could go and say, oh, I'm going to average these over here, or I'm going to concatenate them. And those are all great ideas. 100% true. But there was no kind of very clear way to include it. And so Badanu just said, I'm just going to decode from left to right. Okay. And this just looks like our normal sequence-to-sequence model from the first half, right? But you know where this is going. He then said, well, given the previous latent representation, okay, so ignoring the word I just produced, which is interesting, he's not taking in the word A over here, all right, and updating it. He's just using that HT minus 1. So to answer your question earlier, we didn't even have to use that internal cell of the RNN, it turns out, but Anu said we just have to use the previous recurrence, okay, and we go and we get our score function, whatever that may be for now, okay, and that gives us our context vector. The weighted sum of all of these context representations, the context states, gives us our weighted context vector up at the top over here. Okay, and so you'll realize that now, even though this backwards path of the bidirectional RNN wasn't actually contributing to the decoder's latent state, it is now still being used to get the context vector. So this, number one, did two things. It allowed the backwards pass to only care about maximizing the score for the right tokens. Turns out that was actually deeply insightful, all right? Having this part of the vector space specialized almost entirely to accommodating vector representations in attention is really useful, okay? So Badanu then made that point. They were like, oh, fine, I couldn't use the backwards RNN for the path going into my decoder so well, but it turns out I had then a bunch of free capacity that was all conditioned of my sentence, that was putting up its hand and saying, hey, decoder, I'm talking about cats right now, or I'm talking about mats right now, or whatever. And so that made it really, really good at identifying stuff on the input side. Okay, that was then used to go and predict the next word, and Badanu was using the neural network approach to getting the score, right? So at this stage, they were still kind of throwing the kitchen sink at it. They hadn't figured out where things were and were not necessary, and so they used the most general version of a score function they could. Okay, again, with the benefit of the fact that now you do have the backwards pass to try and help you. Okay, and so you can see we have the forwards pass tokens, the backwards pass tokens, and then what my current, or sorry, my embedding, and what my current decoder is doing. And we just threw that into a big neural network. We had no idea how to actually do this, and so we let the data backpropagation and gradient descent decide. Okay, but now I have a source token, and again, it turned out that that was really precise because of the free capacity of the backwards pass for the softmax. And so now we combine that all with my current word, then the H, and then the context. Okay, so now we combine our three different streams and you predict your next word. Okay, so the only subtlety here, and it's not one that I think really matters too much, so you don't have to worry about it, but you could just keep track of whether or not the attention includes the current word we've said. Okay, in the general formalism, when I explained it earlier, what we would do is we would first compute HT and then use it. In the Badanu model, they didn't use the last word we said. They just used the previous HT minus 1, the previous decoder state, to go and compute attention. So again, there's a little bit of flexibility. It tends to all kind of come out in the wash with enough data, but so on, there are design decisions. And then after that, we can now predict my next word, on and on and on. Okay, so in this case, you have your probability distribution, and that's going to say cat. All right, training it with your usual cross entropy. All right, was cat the right word to say here? Yes or no? If it was, then you take that probability, negative log likelihood, minimize that. Okay, and now all of that information from that one negative log likelihood is going to go backpropped all the way through there. It's going to get backpropagated through here. It's going to get backpropagated down there. And so now we're updating three different streams of representing information. And again, hopefully, when we backpropagate through the attention, it's going to use these backwards pass in the bidirectional RNN to learn parts of the vector space that make it really good at giving you a precise score function. Okay. Leong has a similar model that came out around about the same time. So in this case, they're using your current HT, right? So you do actually have the decoder's last step being introduced into it. So you combine your occurrence and your current word, and then you go do the score, unlike Badanu. Badanu just used HT minus 1. Same idea. You then go and take that updated decoder state, and you go and compare it to all of the encoder states. All right. Leong just used a forward RNN. All right. So now that's a little bit of a loss because we've lost that little bit of flexibility. All of that vector space in the RNN now is carrying information forward into the decoder. And so it's not super clear whether or not some parts of the vector should be used for attention or some should be used for decoding directly. It's going to have to figure that out in the same vector space. Okay. But gradient descent will hopefully do this for us with enough data. And so we end up getting a score function using the bilinearity. All right. So this is interesting because neither of the two initial attention papers used the dot product. One used the bilinearity, which is again just a generalization of the dot product, but a little bit more precise. And then the other one used a full neural network to get the score. So again, the ideas of attention of transformers were all sitting here, but it was very computationally intense. We had a lot of parameters around it, and it was still recurrent, meaning we couldn't churn through a lot of data very quickly because I had to go one word at a time in my decoding. Okay, you get the score, and then from here, you use your current state of your decoder, HT, you combine it with that source context. Now you only have the two vectors. You just concatenate them and predict your next word. Okay, so here we just need to update this notation a little bit differently because we've already said we have our current latent. So now it's our current latent updated by the attention. All right, so that's just the tilde there. You don't have to worry too much about it. You then just concatenate them and go and hopefully throw that into a next word classifier trained with cross entropy, back propagate all of it, and you'll train your model. Okay, you can see it there. They use the tan H and stuff like that. Their actual classifier was also a little bit more general. Okay, but it just used the concatenation of all the information we have. Okay, and then from here, what they did. Okay, and then they started the whole kind of, this paper at the bottom here started the whole emphasis on, can we look at what the attention is doing? Okay, and so what this shows you, the brighter colors are positive values, the duller colors in black are obviously lower or no values. And so all they did was go and map out for every single word when I was decoding it, what were these values here, or at least what were these values here? How much weight did I give words on the input sequence when I was needing to decode it on the output side? And what you will see is that when I want to decode words like the, it was looking at le, right? For at least French text, and please do not giggle at my French accent. Okay. Then if you wanted to do things like speak about the European Economic Area, well, in French that goes backwards. And so it would figure out to look just at that little sequence backwards, all right? So the word area attended to zone or zone, whatever you pronounce it, all right, and so on. And European would attend to European, and then economic would attend to economic. And so you always had this mapping where it was going and finding the exact word it needed to on the context to help it decode on the decoder side, all right? So this one-to-one mapping coming out of the attention is exceptionally precise and very insightful, okay? This means that with enough data and given a really good representation, with enough data and given this opportunity to find good representations, it will do it very precisely because of the soft maps, okay? This was a huge support for attention. The fact that it was this clean was very unlikely. There was no way for the field to predict that, and it ended up happening. And now what you will see a lot of, at least maybe in the first few years of transformers, is the fact that this capacity to look at the attention heads is essentially how we drive all of our interpretability. Okay, all of mechanistic interpretability corresponds to something like this. Where is my neural network looking for information when I give it the opportunity to, and why? All right, and so we'll look at these a lot more as we go on. We'll see a lot more attention maps. Okay, that's all for today. If there's no other questions, I'm sorry about my Slack messages. If there's no other questions, we can leave it there. Yeah. Oh, it's roughly the same. Yeah, what I taught you was the general way of doing, like the most general way of doing it. And then they all have their slight variations. So the slight variations are in what's the score function and how do they use HT. So either they use HT -1 for the attention and then update all three of your streams for prediction, or they first do HT gets updated with my previous word, then I do attention, then I use both those two things to do next word prediction. But it's just about which vector, HT or HT -1, does the attention mapping, what's the score function, everything else is roughly the same. So just to be clear, I taught the general mechanism of attention in RNNs, and the Badanu and the long models are from the literature examples of how that started. Yep. Examples that you need. Yeah. Yeah, so I mean, you have written example questions already. I may just need to update them. I can't. I'll go and have a look. I may add a few more in the next day or so as well. And there's one of them that references something that I've taken out of the class. But yeah, that's there to help you calibrate. Just note that this stuff isn't in your test, right? Okay, the test is up to last week. Cool. All right. Thanks, everyone.